All right. Welcome, everyone. Thank you for coming to our seminar. And it's a pleasure to have here Dr. Mauro Maggioni from Duke University. Dr. Maggioni received his PhD in mathematics from Washington University in St. Louis in 2002. He joined then Yale Mathematics Department as a Gibbs Assistant Professor until 2006 when he joined Duke University. And he's now their Assistant Professor in Mathematics and Computer Science, and his research interests lie at the intersection of harmonic analysis, learning, graph theory, and signal processing. It's a pleasure to have him here talk to us about some of his recent results in high-dimensional data mining. And it's a pleasure to have you here. Thank you.
Thank you very much for the invitation. And as usual, I probably try to cover too much material, so I probably won't be able to. So feel free to ask me questions and interrupt me. It's hopeless to go through the whole talk, I think, in 15 minutes or so. I wanted to sort of share with you some very recent work. Some of it is still unpublished, but I think it's interesting and it opens up many possibilities. And I would like to hear, also from you comments about the possible applications of this work. We're just starting to really apply this to several different venues that I will discuss at the end. Many of you are probably familiar with the problems that arise when you try to analyze very high-dimensional data sets. So I'm not going to talk about many details here, but I wanted to discuss a couple of examples of what we mean by high-dimensional data sets. And this will be recurring throughout the talk. One might consider, for example, a bunch of documents. Here we consider a data set of only, say, 1,000 articles from Science News. These articles cover different topics in science. There are about 9 different fields that are covered in these publications. And you can think of each of these articles or documents as a high-dimensional vector. One way you can map a document to a high-dimensional vector, and this is only the simplest, most trivial, and probably not the best way of doing this, but you could do the following. You can fix a dictionary. Here we fix a dictionary of about 1,100 words. And for every document, you read the document and you count how many times each word in the dictionary appears. And the ith coordinate of the document is how many times the ith word in the dictionary appears in that document. And if you do that, you get what is called a document word matrix, where the column, here unfortunately the number of words is comparable to the number of documents, but every column is a document, and the ith entry of the jth column, the jth document, is how many times the ith word appears in that document. You get matrices like this, and you look at such a matrix, and you don't see anything there. You don't see the 9 topics that are covered in these articles, and it's just a mess. And you would like to make sense of data matrices like this. What does it mean making sense of these things? Well, you might well ask a question: can I automatically discover that there are 9 different topics in this set of documents? Or maybe that's impossible without further information, or it's just too hard. So maybe we can ask an expert to label some of these documents. But the time of the expert is expensive, so we wouldn't like the expert to label many documents. And if he labels only a very small number of documents, how can we use this further information to infer the labels of all the other documents? What is called transductive learning or semi-supervised learning. Another task that you might want to accomplish is that you can think of this set of documents as a point cloud in a very high-dimensional space of word frequencies. If you have 1,100 words, this point cloud is lying in 1,100 dimensions. You can visualize this point cloud. I mean, if you visualize it like a matrix, you don't know what to do with that. So are there more useful ways of visualizing such a collection of documents in such a way that you can browse and navigate through it and find things that are of interest to you? Another example of a data set, this is a standard data set, particularly maybe simple by now, data set in the machine learning community, is a set of pictures, very small pictures. They are just 28 by 28 pixels. And they're pictures of handwritten digits from 0 to 9, they're grayscale. And here are some examples. And we have a database of about 60,000 of those. And so it's a point cloud of 60,000 points in R to the 800 more or less, 20 squared. And so it's a point cloud in 9 dimensions. And one typical task would be to recognize the digit corresponding to these features. For example, for reading checks or reading zip codes. This comes from SPS. Okay, so this was our document matrix. One can ask, can I do something like, sometimes it's called dimensionality reduction or manifold learning. Can I embed this point cloud, which lives in 1100 dimensions, down to 3-dimensional space? Many people have worked on trying to solve this problem. And, you can get nice, quote-unquote, visualizations of these data sets. You can embed them down in pretty low dimensions, and you'll get pictures like this, where each point over there is a document. It's being mapped linearly down from 1100 dimensions to 3D. And I also color the points, but the color was not an input to the algorithms that computed this map. And the color is the topic of the document. And you tend to see that documents of similar color tend, roughly speaking, to cluster together. This is another slice in the low-dimensional embedding. This set of documents embeds pretty nicely in something like 12 to 15 dimensions. And, these features might be already more useful for you to browse, because if you're browsing in this region, then you're browsing mostly on anthropology and biology. If you're browsing in this region, you're browsing mostly documents in medicine and so on. And there's been a lot of work in this type of techniques. And one typical application would be to do clustering in this low-dimensional space rather than doing clustering in high dimensions. And you could do the same thing for digits, and you'll get pictures that will look like this. These are 2 3-dimensional projections of this about 800-dimensional data set. And each point is one of those pictures projected down, and the color is the corresponding digit. And you do see that different digits correspond roughly to different regions of space, but there are regions of confusions, of course. Ones and fours can sometimes look alike, and so on and so forth. And you might think that you could do clustering or labeling in this space and then get reasonable recognition. One of the points that I want to make in this talk is not going to be, I'm not going to talk about how these maps were generated or about manifold learning, but I did do a lot of work in this. But what I want to sort of extract from this picture is the idea that these data sets lie in very high dimensional spaces, but they do have some geometric structures. And these geometric structures, at least looking at these pictures, which you should always be very wary of, because it didn't make any promises about these pictures. Do they respect the geometry up there? Do they completely destroy? Who knows? I haven't told you anything. But I claim that, in fact, they do respect somewhat the geometric structure of the point cloud in high dimensions. And they do reveal that there are low-dimensional structures in the data. And so I often like to think of this data set as being intrinsically low-dimensional point clouds embedded in a very high-dimensional space. And there is noise, which sort of tampers with the geometric structure of the data. But intrinsically, the data has fewer degrees of freedom than it seeks. Think about text documents. Certain words appear with high frequency, then the topic of the document is decided, and many other words are going to appear, and other words are not going to appear. And this is simply saying that the coordinates are very dependent. So there are not 1100 degrees of freedom, but there are far fewer. If you think about a digit, if you know that certain pixels are white, you know that certain others have to be white, or they're white with very high probability, and some others are black. There are, again, constraints between coordinates, and the intrinsic dimension of the data is much lower than the data. And many people have worked up this idea in the past 10 years, and it might be surprising that we don't have really a good way of deciding what's this intrinsic dimension. So the first topic that I wanted to discuss today, I'm going to skip the physics example, but maybe we'll get. If you're interested, we're applying these sort of techniques also to molecular dynamics simulations. If anybody's interested, I can talk about that as well. And so I've been doing a lot of work with many different collaborators on analyzing these low-dimensional data sets in high dimensions, and much of my past work has been about the following set of techniques. You model this point cloud by a graph, where you connect each data point with its neighbors, and then this graph now is sort of intrinsic to the geometry of the data. The geometry is some sort of manifold structure, some sort of low-dimensional structure. This graph is an intrinsic graph that lives only on the data because it only connects data points. And then looking at the structure of the graph by using random walks or eigenfunctions of random walks and tools like that. What I spent my last year developing are a new set of tools where that are not related to graph theory, but this is a set of techniques that tries to work in the high-dimensional space but building and managing lots of low-dimensional structures in the high-dimensional space. The motivation for looking at the graph structures, remember, is that you want to build something which is intrinsic to the data. But then, you reduce the dimension, and then it's always hard to go back to the high-dimensional space. You build these reduced models, and then it's very hard to invert that. Say, from a low-dimensional set of coordinates, these techniques typically have a very hard time with giving you back high-dimensional points. And people have some techniques, methods, extension methods, and I don't think they work particularly well. So I said, well, maybe we should not be afraid to work directly in the high-dimensional space, provided that we do things in a computationally efficient way that takes advantage of intrinsic low dimensionality. And that's been the focus of about a year of work. And I started by asking a very simple question. So we keep talking about this intrinsic low dimensionality, but do we know how to measure it? And I looked up the literature, and I was partially unsatisfied, and I decided that it was still an open problem. So the first thing I wanted to talk about is how to estimate the intrinsic dimension of data. And then maybe, depending on time, I might skip two, but then I do want to talk about it. Okay, so why do we care about intrinsic dimension? Because it's I think it's a very fundamental question. It is sort of asking how many degrees of freedom does the point cloud really have? If it is a manifold, what's its dimension? Is really telling you how many free parameters you should be discovering. But if it's a physical system, maybe this is a complicated molecule moving around, there's many coordinates, a very high dimensional space, but maybe the set of configurations is a low dimensional manifold in there, or maybe the set of interesting configurations is a low dimensional set. And discovering the dimension of that is telling you about how many interesting degrees of freedom this high-dimensional physical system really has. And if this number of degrees of freedom is much lower than the ambient dimension, well, you should be able to take advantage of that and do a much better work, a much better job at sort of constructing models of the data from the physical system. If you're building statistical models, all of the time statisticians talk about latent variables. You have very high-dimensional points, but there is a small number of latent variables. Well, the number of latent variables is what I'm calling intrinsic dimension in this talk there. So it comes up in a lot of different situations, and it's always sort of the same. So let me give a very short overview of a huge amount of work that has been done in order to estimate this intrinsic dimension. I sort of beamed the approaches into two different beams. These are very coarse clusters. Volume-based methods and principal component analysis-based methods. The volume-based method is very simple. It says, pick a data point, pick a ball of radius r, look at the data points which are in there, and change r. As you change r, if the data is k-dimensional, the number of points that you get in a ball of radius r should scale like r to the k. Well, there you go. So just do that and count the number of points in balls of different sizes. It should go like r to the k. So if you take a log, the slope of the line that you get should be k. And there are, at least here, maybe 15 papers. There are probably like 40 papers. And when there are too many papers on about pretty much the same idea, it means that it probably doesn't really work. Otherwise, there will be one paper. And what is the sample complexity of this type of techniques? Well, what do I mean by that? Well, you look at the ball of radius r, and you get a certain number of points. Then at a certain point, you might look at the ball of radius 2r. How many more points would you like? You would like 2 to the k more points. You had 10 points here, you want 2 to the k times 10 points in the ball of radius 2r. So I say that the sample complexity, albeit this has not quite been proven, but for those methods, I argue that it's exponentially in the intrinsic dimension k. There is another set of techniques, which is based on principal component analysis. I assume that everybody's familiar with that. Maybe you call it SVD or PCA, it's all the same thing. And the idea there is very simple. If the data lies on a k-dimensional plane, then it's really easy to find k, because you just compute the covariance matrix, you diagonalize, you have k singular values which are large, and the other ones are all 0. And if you have a little bit of noise, so the points are just close to the plane, well, you should have k large singular values and many small ones, and you should be able to still do it. And now, if points are on a curvilinear structure, then, then it's not so easy anymore, because if you just do PCA, you find the plane that contains the whole curvilinear structure. But maybe this is, a one-dimensional structure that navigates many, many dimensions. And so you can't quite do that. And so people said, well, of course, but this is not the right thing to do, because you do PCA globally. You should do PCA in a small region around a point. And then, if you have a manifold, then in this small region, the manifold is roughly flat, and PCA should still work. This was suggested back in the 60s by Handwritten. in 67. Okay, so how many points do you need in order to do this? Well, it's actually interesting. There's been a lot of recent work in estimation of principal components and covariance matrices that tells you that if the data is, on a k-dimensional plane, you only need a number of points which is linear in the dimension of the plane. Why? Very, very roughly speaking. Well, as soon as you have 1 point here and 1 point there, PCA should pick up that this direction is in the plane. If you see 1 point here, 1 point here, you see that this direction is in there, and you know the plane is already 2D. So roughly speaking, as soon as you have about 2 points per direction, you should be able to see that direction popping up in PCA. And so if you have k directions, you should need about 2 times k points. Log by k, there is a log k, because now your directions are like coupons. You have k coupons in order to collect them, you need k log k. But now what about curvilinear structures? Well, you would expect that maybe you need only k log k points locally. The problem is, what does locally mean? There is a scale there that is implicit, and it's completely crucial. Because if you pick a curve like this, and the red line is the top principal vector, and the green line is the second principal vector rescaled by the singular values, depending on the curve, all sorts of things can happen at a scale like this. Here you see that the first principal vector is much longer than the second one, so you would say the dimension is 1. But if the curve was like this, and you keep the same scale, the 2 principal vectors almost have the same length. And if the curve is really curved, then the first principal vector is actually pointing in the normal direction. So everything depends on the scale you're working at. And there were some recent papers by Bruske and others that compared all these dimension estimation methods, and they said PCA-based methods just don't work. And I think the problem is that because scale was not discussed in those methods. So let's see how scale matters. Okay? And I'm not going to go through any of the theorems and proofs. I just want to convey some pictures that I hope you will find intuitive and agreeable. So what we're going to do is the following thing. We don't know what the scale is, and I think the scale is really a fundamental problem. So what we're going to do is we're going to do PCA multiple scale. We're going to do multiscale PCA, which is also a very simple thing. We're not going to do anything next. So suppose our data is sort of on a manifold. We can do structures which are way more general than manifolds, but then it becomes technical, and that's not the point of this one. So suppose we have a manifold. That's the green curve. It could be 5-dimensional, and it's in a high-dimensional ambient space. We pick a point z. We look at the points in a ball of radius z, and we compute PCA. And then we're going to change r, and we're going to look at how the singular values change as a function of r. What should happen? Well, data is never on a manifold. There is always noise. And so noise should be in from the very beginning of the analysis. So when we add noise, the noise is high dimensional. It's like when you take a picture of a digit, the noise is never pixel. So even if the digits might be 5-dimensional, if you have 1 megapixel image, the noise is in 1 million dimensions. So what happens is that the points on the manifold get thrown out and away from the manifold, because with very high probability, the noise is not going to be aligned with the manifold. It's going to be in normal directions. There are so many normal directions. And so what happens is that the points get thrown away from the manifold. How far do they go? Well, it's actually interesting, because when you are in high dimensions, all sorts of funny probabilistic phenomena happen. You have phenomena like concentration of measure that tell you that if you look at the length of the noise, that's almost a deterministic quantity. So for example, if the noise is Gaussian with variance sigma in every direction, the length of the Gaussian vector is with very, very high probability equal to sigma square root of d plus minus something teeny, something that looks like sigma over square root of d. So when square root of d is large, almost all the points go at a deterministic distance from the manifold, in the normal direction. And so I'm drawing this tube, which is in fact has some thickness, but it's almost exactly a hollow tube, which is where the points end up. So the points from the manifold go out in a hollow tube. Does everybody buy this so far? Okay, so I pick a point z, I pick a small radius, r, and I look at all the points which are in that ball. Well, there are almost no points, because the points have gone away by sigma square root of d. So as soon as r is smaller than sigma square root of d, I should see very, very few points, if any point at all. Then I'm going to let r increase. And at a certain point, I start touching this tube. So all of a sudden, I'm going to see a lot of points, but they're going to be in all possible normal directions. So I'm going to see that they are everywhere. And if I compute the SVD of those points, I'm going to get a very high dimensional SVD, because I'm going to get all singular values to be almost all equal to sigma. and they're going to be, and the singular vectors are going to be in all directions. So PCA at this scale is also completely useless. Then if you pick radius, which is even bigger, what happens? Well, the normal directions are not growing when you increase R, but the directions along the tangent directions of the manifold are still growing. I keep getting, I get more points now here than in the normal directions, and so my singular values should grow in certain directions and not grow in the noise direction. And this is a good scale where I can see that there are k large singular values and vectors, and the other ones were only due to noise. And then if I pick R even larger, well, if I pick R even larger, then the manifold starts to curve, and then it's nonsense again, because I start seeing a lot of singular values which are large just because this ball is going to see points which are in different pieces of the manifold, but nothing to do with the piece that we should be concerned with. So there is a certain range of scales in which things work. If you look at different scales, you can get complete nonsense, from 0 to everything, when the ball is of this radius, to God knows what when the radius is too large again. So is this true, or is just a cartoonish image that is not correct? So let me play a very simple game. I'm going to pick a 9-dimensional sphere. I embed it in R100. I had no noise, and I sample uniformly from this sphere. I pick the north pole. I pick a radius R. I look at the points in a ball of radius R, and I do SVD. And as a function of R, I'm going to plot the singular values that I see. So when R is small, I get 10 singular values. Why 10? Well, the 9-dimensional sphere really sits in R10. There is nothing in the remaining 90 dimensions, so I only get 10 non-zero singular values. And that's how they look like. As I increase R, the singular values do something very interesting. Well, at the largest scale, I'm looking at a sphere from far away, and so all the singular values are equal to each other, because I just see a sphere from far away. I can't tell if it's a sphere or a ball. But there is a range of scales where 9 singular values are growing linearly, and the 10th singular value has completely different convexity, grows quadratically, and it's measuring curvature. And if I do PCA here, I don't know what to conclude. The 10 singular values are roughly equal, equispaced, maybe it's 10 dimensions, maybe, I don't know. If I do PCA at that scale, I would say that the manifold is certainly 10D. Look, the 10 singular values are all equally large and separate from 0. But the true dimension is 9, and there is a range of scales where the gap between the 9th and the 10th singular value is the largest gap, and that tells me that the dimension is 9. But if you don't look at the whole picture, how do you choose R? Now, there was no noise here, so maybe when you add noise, everything falls apart. So let's add noise. So I call both the tangent singular values, and I call this the curvature singular values. Let's add noise. Let's add a lot of noise. Okay? So, by the way, sorry, let me make one remark about this example. Okay, so one may say, oh, this is a sphere, it's 9-dimensional, it's not very high-dimensional, everything is trivial. Just a second. But let me claim that this example already is non-trivial. We have 1,000 points uniformly sampled on this sphere. The sphere is 9-dimensional. It lives in 10 dimensions. In 10 dimensions, there are 2 to the 10 orthons. So the 10th is 1,000. We sampled 1,000 points. So we have about 1 point per orthon, if that makes sense. With 1 point per orthon, we see curvature. You usually think curvature, second-order object, it takes a lot of points to estimate, it's very unstable. Not in this sense. With 1 point per orthon, we measure curvature. So in a certain sense, there is something sort of crazy going on.
Yeah, so according to your cartoons picture in the previous slides, you're saying the eigenvalue you observe in the normal direction should stop growing.
Correct. So here it's growing. Yeah, so actually, maybe I should have plotted since R equal to 0. Here, R is already kind of big. Okay, so R does almost nothing. But then, yeah, I should have maybe added 2 scales to my cartoonish picture. So the smallest R that we see in the next slide is sort of around here. And there was no noise. So and then as you enlarge, you start seeing the manifold curving. And then this singular value will start growing because you start seeing that the manifold is not quite flat, it's bent. And so there is something in the normal direction. But that something is growing quadratically, not linearly. So maybe I should have drawn one more scale where you do see that this slight curvature of M actually plays a role and increases the normal singular values quadratic. And now let's add noise so that we see whether a cartoon image was correct or not. So I kept the range of R here is slightly different. This is roughly the same as in the previous picture, but now R becomes much bigger. So what is this data set? Always the unisphere, but then I had Gaussian noise in 100 dimensions of variance 0.1 in each direction. This is a lot of noise, because 0.1 in each dimension in 100 dimensions means that the size of the noise is 0.1 times the square root of 100. That's equal to 1, which is the radius of the sphere. So it's a lot of noise. Now when R is small as before, nobody's there, and all the singular values are 0. Then all of a sudden, I see lots of points in lots of different directions. If I look at this value of R, then I start seeing the cube around me. It's nonsense. And I take R bigger. Look at what happens here. The size of the noise goes to 0.1, the one-dimensional size of the noise. 9 singular values growing linearly, and the 10th singular value growing quadratically. So even in a sphere in 10 dimensions with only 1 point per quadrant, moved in a random direction by something which is like the radius of the sphere, we see curvature, and we see that the correct dimension is 9 in the correct range of scale. So there are tangent singular values. There is the noise. And the noise singular value is 0.1, not 0.1 times the square root of d. It's just 0.1. This is really good news for us, because it means that this is independent of the ambient dimension. And then we can even see curvature. All right. But of course, if you choose the wrong scale, well, who knows? You can get any result that you like. And we like to sort of have sort of phase portraits of what's going on. We have a plane of R, and the size of the singular values as a function of R. You can plot this as a picture. And you do see that at the small scale you have noise, and the larger scales you have 9 and 10 dimensions playing against each other. So if you look at this picture, you might say, oh, well, we're sort of independent of the ambient dimension, because the size of the noise that we measure is sigma, not sigma square root of d. But we should be cursed by dimensionality. Well, it's not the ambient dimensionality that is going to curse us. We're going to have a curse, but it's going to be a curse of the intrinsic dimension. So as the intrinsic dimension k grows, a funny phenomenon happens. So actually, let me now go to the next slide. So let me ask you a question. So suppose you have a sphere. You sample as many points as you like, and the sphere is k-dimensional. What is the covariance matrix of the set of points on the sphere? Does anybody want to guess? You can sample as much as you like, okay? So you have 1 gazillion points on the k-dimensional sphere, and you do SVD. How large are the singular values that you're going to get? And what is the covariance matrix? It's diagonal. It's rotational invariant, so it should be like the identity. It is the identity times a very important factor, 1 over k. 1 over the dimension of the sphere. So the higher dimension of the sphere, the smaller its covariance matrix. That's the curse of intrinsic dimension. That is saying that if you fix the value of noise and k grows, for k large, the covariance matrix of your signal, of your manifold, is going to fall below the noise. And you're not going to be able to see your manifold. Okay? Just for fun, you can really compute this. You can take tons of points on the k-dimensional sphere, and you can look at the largest singular value or the gap between the singular values, and they decay exactly like the covariance of the k-dimensional sphere is 1 over k times the identity. So your signal to noise ratio goes down as k increases, if you want, with geometric signal to noise. And this is very well known. Geometers in high dimensions know this phenomena very well. The density concentration of measure, observable diameters, and so on. If you look at a very intrinsically high dimensional object, then it looks small, no matter what you do at it. And for the sphere, we can predict anything, and there are lots of interesting phenomena there. Maybe an interesting time. I'm not going to discuss. And then, we can analyze our algorithm and try to decide, try to prove something along the following lines. First of all, we want to prove that the features, this behavior with singular vectors that we exemplified in the simple case of a sphere and so on, is actually what happens in general. And then we want to prove that this happens with that the picture is correct with very high probability over the sample of points and the realization of the noise. And then we want to count how many sample points do we need before the picture becomes true with very high probability. And the answer is that you only need a number of points which is linear in the intrinsic dimension of the manifold. So under reasonable assumptions, the manifold doesn't curve too much, the noise is not huge, then we can prove that as soon as the number of points in a ball of radius r is like k log k, where k is the intrinsic dimension, then if you go and compute the singular values empirically on both points with that noise and so on and so forth, then you're going to get the picture that, like in the previous slide. And if you have the picture, then you can go and design an algorithm that goes and estimates the size of the noise, estimates the, which singular values are growing linearly, which ones are growing quadratically, and can tell the dimension of the manifold. And I don't even know whether I included the, yeah, I'm not going to go through the correct statements because again, we don't do manifolds. And manifolds are sort of a zero-order approximation of these things. Data sets are not really manifolds, except that in very rare cases, we do geometric structures which are much more general than manifolds, and we essentially don't pay a price. This algorithm is very, very robust to noise and sampling, as you already saw. I mean, we could measure curvature in an object which was crazily undersampled and crazily perturbed by noise. So they don't care about smoothness. So we can do things which are much more general. But the point is that we only need a number of points, which is minimal. It's only linear in the intrinsic dimension. Right. And once we're that, we actually have an algorithm that, picks a point z, picks a ball of radius r, looks at the points inside, computes the singular values. And then, with high probability, we know that unless we have very, very, very few samples, we get pictures like this. And then we can go here and estimate the size of the noise. Once we know the size of the noise, we can sort of backtrack these noise curves and look at the first scale where the noise is small compared to the average singular values. We don't want to be here when the noise has corrupted everything. So we backtrack the noise and we stop here where the noise starts being small compared to everything else. And then we go up in scale again and we say which singular values are growing linearly, which ones are growing quadratically. The ones that grow linearly are about tangent spaces. The ones that grow quadratically are about curvatures. So we can tell which dimension. Oh, and we care about having algorithms which are efficient. We say, oh, this can be efficient. You're computing SVDs like crazy at all scales, at all points, and so on. Well, you can organize the computation in an efficient way by not sampling all points, by sampling points on nets distributed correctly at different scales. You don't do full SVDs. The data is intrinsically low-dimensional, so you need only to do low-rank SVDs. And for low-rank SVDs, they are very accurate and yet very efficient randomized algorithms that take advantage of intrinsic low-dimensionality. So the whole process only takes a number of operations, which is order size of the matrix, n points in capital D dimensions, log n. And this capital K is a parameter that you feed to the algorithm, and it says it's an upper bound of intrinsic dimension. So you say, I'm not interested in things which are more than 50 dimensions intrinsically. Then you will set K is equal to 50. So it's an upper bound of the actual dimension. We usually use K equal 100, but we really don't care about things which are more than 10 or 15 dimensional. Intrinsically, that's the intrinsic dimension. And we run multiple tests with lots of different algorithms. I like to compare things. So we start with completely trivial things like cubes. You would think that the problem of estimating the intrinsic dimension of a cube is completely solved, and it was kind of shocking for us to find out that it's not. So we pick a 6-dimensional cube. The second number, 250, is the number of points. I embed it in 100 dimensions, and I change the size of the noise from no noise to lots of noise. And the true dimensionality is 6, no matter how much noise you add, right? And then all the curves, except the correct ones, are algorithms which are not ours. So they're sort of in the ballpark for no noise, and they completely take off in the overestimated dimension when sigma increases. You can do 6-dimensional cubes, 12-dimensional, with more points, with less points, higher dimensional. The same picture always arises. In the cubes, and the spheres, same problem. Our algorithm, which is the right curve, is almost always correct, except sometimes when you add a lot of noise. 0.1, again, means size of the noise equal to 1, compared with the radius of this. We can even do a 24-dimensional sphere, so it lives in 2 to 24th orthons with only 2,000 points. So we don't even have 1 point per orthon. We're far from that. And nevertheless, up to, say, noise, which is half the size of the sphere, we can predict very well the intrinsic dimension. The other algorithms are scattered all over. Okay. And so most of them are volume-based methods. Other ones are actually state-of-art Bayesian methods that try to estimate the dimension. Those really like the numbers between 1 and 4 for one reason. Those are last papers from last year. Maybe the problem is that we had noise. So let's look when we have no noise. And let's look at all the methods for the data sets before with no noise. The blue numbers are the only correct ones. So this is scary. Okay? So only the last column, which is our algorithm, is correct almost all the time. And the other algorithms often are all over the place. Okay? It's kind of worrisome. These are cases that we get wrong sometimes with probability, say, half we fail. This is a 47-dimensional sphere with 4,000 points on it. You see the curves of intrinsic dimension? The covariance is 1/k, so these singular values are all very small. You can kind of see curvature there. You can sort of see that this is a good range of scale, but the algorithm gets it wrong about 50% of the time. Let me not talk about the other example, but this example is about a one-dimensional curve that turns around in all possible dimensions. So it has lots of curvatures in all dimensions. And then in a range of scales, it does look like a one-dimensional curve. But then once it has spiraled out into many dimensions, it looks like garbage. Algorithms go crazy about this. We apply to real-world data sets like the handwritten digits. There we don't expect the dimension to be constant. So what we plot is how many points have dimension 1, how many points have dimension 2, how many points have dimension 3, and so on and so forth. And we get histograms. So for handwritten ones, many digits have dimension 1, most of them have dimension 2, some of them have dimension 3, and so on and so forth. Well, I think it really corresponds to the local intrinsic complexity of the data. So if you look here, these are the ones which have no little thing at the top or at the bottom, are the simplest ones, and the only degree of freedom is rotation. Then there are ones which have the squiggle at the top, the squiggle at the bottom, and can vary in many directions locally. And those are the ones with higher dimensionality. And if you look at more complicated digits, like 3s, they're region of space where they have many degrees of freedom. And sort of, I think we're sort of measuring in a rough way this sort of phenomenon. We can look at other data sets which are standard in machine learning. Isomap, these are movies, and these are the text documents that I discussed before. Text documents are weird. They're totally weird. They're the most interesting of all. So there are lots of documents of dimension which is about 2 or 3. And then there are documents which locally are very complex. They're 10, 20, some of them even 80 dimensions. They're totally non-linear, and this dimensionality varies there. Same thing in molecular dynamics. And we can do sort of mixed manifolds and things like that. And here I sort of show that if you just do standard, you see, the intrinsic dimension is an input to almost every manifold learning algorithm. And so people even say, pick your favorite manifold learning algorithm, just try 2 dimensions, 3 dimensions, 4 dimensions, and so on. Then at a certain point, you should see somehow the singular values drop. But it's just not true. Here we show that, for example, you pick isomap, and you look for gaps in the singular values. Even for trivial examples, as soon as you add a little bit of noise, there are no gaps. You cannot tell what the dimension is. And we timed everything. The algorithm scales as theoretically predicted by the theory. The algorithm scales linearly in the number of points. And somehow surprisingly, this is a plot of the time that it takes to do various pieces of the algorithm as a function of the intrinsic dimension. And what we see is that the complexity increases very, very slowly in terms of the intrinsic dimension, which is kind of nice. Because that could be. So this was, in a certain sense, step 0. Then we moved on to the following problem. But maybe I'm going to skip the discussion on this for the sake of talking about 3. But many people have tried to model data sets as lying on a union of planes. And the standard approach there is saying, well, I don't know these planes. Let's assume I know their dimension, maybe. That's a common assumption. And let's assume that I know how many planes I want to use. Then how do I fit this number of planes of this dimension to the data? Well, you can write down optimization problems, and you can try to solve them. Well, we said, well, maybe there is a different way of doing this. And we developed an algorithm, and we proved that it has very good properties, that works in the following way. We pick a point, we look in a neighborhood, and we estimate the plane in that neighborhood by looking at exactly at the multiscale SVDs around the neighborhood. And so we find a neighborhood, and we fit a plane. And then we ask, does this plane explain all the data? No. Okay, let me pick another point. Let me pick a local plane. Now I have two planes. Do we explain the data? No. We keep doing this till the data is explained. And we have proxies for what it means to explain, and so on and so forth. And we stop when we're done. Now we have a lot of planes. Maybe we have too many. Maybe sometimes we pick points which were already on a previously picked plane. Then we merge these planes together, and that's our answer. And we can prove that with a very small number of points, this procedure is correct. Let me leave it at that. We publish this as applications to face recognition, motion detection. The people in computer vision use this type of technique a lot. There is a pretty big literature, except that everybody is doing this sort of global convex optimization method. And our method is completely different, and it has guarantees. And we don't need to know the dimensions of the planes. We estimate it by the previous algorithm. And we don't need to know even the number of planes. So we're doing both model selection and actual fitting of the model. And the results are very competitive. And in fact, there are almost no algorithms that don't require the number of planes and the dimensions. So just because of that, we're doing better than most of the competition. And then we apply this to face recognition to a simple database. We're trying to do more complicated examples right now. And the results are very promising. So I went fast for that because I wanted to tell you about the very latest things that we're working on, which are related to modeling data sets by planes. But when you say, I want to model something by a union of planes, but if you want to model, you should have some other parameter, right? You should say maybe what the number of planes is, but that seems artificial. How do you know how many planes you need? Maybe a more natural parameter is saying, I want to approximate my data by a union of planes up to a certain precision, so that if I approximate my data by projecting onto the nearest plane, I don't make an error bigger than epsilon. And then the epsilon is maybe a natural parameter because you know what the size of the noise is and you know how to set your epsilon for things like that. But then if you change this epsilon, the planes are going to change. So suppose I want to send you a database or a point cloud whose points are the points in the database, and you say, okay, just send me a sketch of a database. I send you a coarse approximation, like setting epsilon like a half. Then you see a portion of the database that you really like. You say, oh, I think that what I'm interested in is over here. Well, I should be able to send you more information that reduces that, does epsilon 1/4 in that region of the database, and so on. And we know how to do this for images, for one-dimensional functions. You do wavelet expansions, multiscale expansions. When you download, say, certain types of JPEG pictures from the web, you see, at least when the connections were slow, you see the multiple resolutions forming because the bits are sent you in a multiscale way, if you want. We would like to do the same thing, but for a point cloud, for a whole database, not for a one-dimensional or two-dimensional function. And this fits into a pretty hot topic, which is called usually dictionary learning. And what is dictionary learning? Well, vaguely speaking, it's motivated by the following. For one-dimensional signals or 2D images and so on, we think we have pretty good models for these images. And people have spent a lot of time building essentially by hand, dictionaries of functions, curvelets, wavelets, wedgelets, shearlets, you name it, for analyzing, too many lets, to analyze these signals. Because we sort of believe we have good models. Whether that is true or not, I won't comment, okay? And then you design fast transforms so that you can compute with these things. And they've been used all over the place for compression, denoising, interpolation, painting, you name it. Then people have observed, maybe we can learn these dictionaries. We don't have to work so hard. I'm coming from the school of building these dictionaries. And it takes it takes hard work to construct those and the corresponding fast transform. Maybe we can learn them from data. So we can stare at a few images, and then we come up with a dictionary good for those images. And if these are natural images, maybe we come up with wavelets, and it's not interesting. But if these are faces, then the dictionary for faces should perform better than a dictionary which is for all natural images. Or a dictionary for GMRAs or stereotype types of GMRAs should work better than a general purpose dictionary. So lots of people have started working on building data adaptive dictionaries. They started with maybe Dono and in the sort of computational harmonic analysis community, but it goes all the way back if you want to doing SVD for time series. Okay, and it has lots of applications. It has with sparsity and so on. Just to formalize the problem just a little bit, suppose we have a data set X. It's in RD, D huge. We want to construct a dictionary. What's a dictionary? It's just a bunch of capital D dimensional vectors. We're going to pick M of them. And then we want X to be well approximated by phi times alpha. So the columns of phi are the dictionary elements, say facelets. Alpha, we want it to be a sparse vector so that every face is a short linear combination of a few facelets, up to a certain precision epsilon. And you look at the problem in this way, so you see that there are many numbers there. There is the M in dimension, okay. But then there is the size of the dictionary, M. There is the sparsity of alpha. The sparser the alpha, the happier we are. And then there is the precision epsilon. So for example, if you fix the precision and you increase M, the number of dictionary elements, you would expect alpha to become sparser. So for example, I could pick phi equal to X, then alpha is the identity, and it's really, really sparse. Oh, but then phi is too large, right? So what are the relationships between M and epsilon and the sparsity of alpha? Nobody really knows. Okay? We know for classical wavelets and curvelets and simple models, but we don't know in general. And none of the existing dictionary learning algorithms have any sort of guarantee. So we try to approach this problem from a different perspective. We say, let's put some geometric assumptions on X, like X is intrinsically low dimensional. Then we come up with a way of constructing dictionaries which has guarantees on the sparsity of alpha, and the computation of the dictionary is fast. None of the current algorithms are essentially saying, you write that down and you optimize. You fix the size of the dictionary, you fix your epsilon, you optimize over phi and alpha. Very expensive. There are fast algorithms in practice sometimes, but in general, very, very slow. We come up with a fast construction of the phis, of the dictionary itself. Now, given the phi, it is not trivial to find alpha, because the phi is typically redundant. M is typically larger than capital D. You want redundancies in the phis to achieve sparsity. You want the sparsest alpha such that the alpha is close to X. So finding the alphas, even given phi, typically is computationally very expensive. It's like solving a big lasso problem, or by orthogonal matching pursuit or stochastic gradient. These algorithms are expensive. Not only the construction of the phis that we do is fast, but also the computation of the alphas is super fast. It's like a Wavelets transform in the language. So and I like to do simple things if they turn out to work. And so the construction of the dictionary is very simple. So let me skip this. This is sort of a one-page, ultra-short review of how people think about this problem, which kind of optimization problems they try to solve. And if you look at them, no matter what the symbols really means, it's really complicated. This part seems convex, but then the optimization happens on non-convex sets, and the whole problem is non-convex. And lots of references. This is a teeny snapshot. Okay, so we do the following thing. Let me actually go by picture. I like pictures. So we're going to do the following. The algorithm has 3 stages. The first one is partitioning. Okay, so think of the data as being on a manifold. I'll bite again. This can be generalized. Great. So the point up there of the tree, each node of the tree right now is a piece of data. The node at the top is the whole data set. Then we chop it up into 2 pieces. Those are the 2 nodes, and each piece we chop up in, say, 2 pieces. Those pieces we call CJK. CJK is the piece at scale J in the tree, and sort of location K at that level. In each of the pieces, we do PCA. So we have a linear approximation to the data. And so at scale J, if you fix J, you have a bunch of planes, pieces of planes, that approximate your data set. And as you cut into more and more pieces, you would expect these linear approximations to get better and better. But now, it's sort of expensive to keep track of all of these approximations at different scales. And if you think about it, suppose you're sitting in this piece, and you have a linear approximation to the data. Then you cut this piece into 2 pieces, and you do linear approximations. Well, these 2 linear approximations should be pretty close to the linear approximation that you had above. So what we're going to encode are not these linear approximations, but we're going to encode the linear approximation at the father, and then a sort of difference that will give you the linear approximations of the children. But this difference is what is small. It's like in wavelets, for those of you that are familiar with that, you have a certain approximation on one scale. If you want to go to a finer scale of approximation, you just transmit the detail. What you need to add to get the farther. And this is a geometric version of all of that, where things are happening in high dimensions, but these planes are all low dimensional, because the data is intrinsically low dimensional. And these corrections to go from one scale to the refined scale are also low dimensional. And here is another picture where you think, your data is like on a manifold, with one big plane approximating this big chunk. Then we divide the, and this plane is spanned by certain functions that are like scaling functions. We call them Pj, at scale j. Then we cut the piece into two pieces. We have two planes. We get the Pj plus 1, the children scaling functions to those. But we don't encode those. We encode sort of the normal differences that are needed to move a point x projected at scale j, that's xj, onto its finer scale approximation. That difference is small, and it's what we encode along some quote-unquote normal plane, which we call a wavelet plane, and we call Pj plus 1. And now every point can be written as a coarse approximation plus a number of corrections. And these corrections become small very quickly, depending on the geometric structure of the manifold. And our dictionary is going to be made, so suppose this manifold was a manifold of faces. Well, these planes are planes in the space of faces. And the Pj's are vectors in both planes. So the Pj's are faces. And the Cj's are faces too. So we're building a dictionary, and every face can be written as a coarse face plus correction to the coarse face. And so this is how we build dictionary. Let me go. The algorithms are really short. This is pseudocode for the whole construction. And you can map every point to its coordinates on this multiscale structure of planes. That's 2 lines of MATLAB code, seriously, and it's fast. And also the inversion is fast. We can compute we can look at the computational complexity of everything. And the point is that everything depends only on the intrinsic dimension of the manifold. We're working in high dimensions, but the computational cost is something like the size of the data matrix and points in capital D dimensions, and everything else is either logarithmic in n or only depends on the intrinsic dimension. Let me forget about all of this, and let me just show you two pictures. One is trivial examples, like a Swiss roll, an S-manifold, or something that oscillates more and more. And we can produce multiscale approximation to that. That's a coarse picture of the database. You ask me for more information, suppose everywhere. I can quickly send you the data for that. And this is how the arrow decays. It decays quadratically for manifolds. And if manifolds are complicated, in certain regions, the approximations get better faster. In some regions, it gets better at a slower rate. And we obtain new data representations where we can list the points horizontally, and vertically we can plot these coefficients, these geometric wavelet coefficients as we call them, and white means 0. So these representations are very small. I know I'm not giving you a lot of details, but let me show you, for example, the case of faces. So we can fix a face, and we can plot how it gets approximated at multiple scales. And what you see is that at every scale, we have a face. So if you are doing wavelet transform or curvature transform and you truncate the expansion, you don't get faces, you get nonsense. But here, because we're always close to the manifold, at every scale we have a face. It's a generic face at the beginning, and then it gets refined into the final face. And we can ask, what were the elements of a dictionary used for this face? And here they are, from coarse elements to finer and finer elements that fit in. And in this table, from coarse scale to fine scale, we plot the dimensions of the planes that we use. And these dimensions vary from place to place. This is very complicated. Well, it's not very complicated, but it's a complex data set. It's not a manifold. The dimensions vary from location to locations, but they're always between, say, A and 1 in most places, except in a few places where the dimension is much higher. Who knows why? Complicated space. And let me stop here because I'm running out of time. But we ran this for image patches, for example, and we get dictionaries which are hierarchically organized. And the transform on this dictionary is always fast. If the intrinsic dimension is small, the transform is always fast. So I can stare at patches of images. I get a fast transform of my dictionary for free, which is totally crazy, right? I mean, you build wavelets. Building a fast wavelet transform is not that easy. It seems easy nowadays, but it was not that easy. The curvature transform is even harder. There are other transforms which are very useful, for which it's really hard to construct fast transforms. In this case, they come for free. For example, almost for free, we can produce an FFT. And then we look at how well we compress these data sets or these databases. And we're starting using these to generate new faces, new handwritten digits for building models for data. And I'm going to stop here. Thank you, and I'll take questions, and I'm going to stick around for a couple of hours to talk with as many of you as possible.
From the intrinsic,
yes.
From the very beginning of the talk, are you able to use things like persistent to get these ranges or anything like that?
Oh, yeah. So actually, John Harder in my department does a lot of that. And so we are discussing how to sort of merge the two approaches. So can you use these to tell you something about the scales and then inform the topology, and conversely, when you see the topology changing, decide that you should stop the range of scales. We don't know how to do that, but it seems like a very natural idea, because this is totally blind to the topology. Right? It's just looking at how these linear approximations look like. On the other hand, it's very robust to noise, so maybe that's useful for the topological method. How do you go back and forth and do this? It's a very interesting question. They recently wrote a short paper on trying to use sort of random walks type of ideas to do their persistence homology. So rather than using these distances and distances in the ambient space to build these simplicial complexes, they use sort of diffusion-like distances on the space of points. And the results are promising, but it's still different from trying to tie things in with this sort of system. So it's a very good question.
Your talk.
Yes.
Have you published this stuff?
We just submitted like 3 days ago. I can send you the paper.
Yeah. It'll be interesting. There are a lot of things that I missed.
Yeah, I'm sorry. I sort of squashed it a lot.
But it looked actually very interesting and fascinating. So we'll have a chance actually to talk a little bit more. If there are no questions, we'll just basically take it offline and go through. All right, let's thank our speaker.